Hello and thank you for joining us. I am Kyle Chester. My partner is Alec Van Slooten, and we are doing a senior design presentation on the computational analysis of solid propellants. Our faculty advisor was Professor Xinyu Zhao, and our sponsor was Patrick Meager. Our project definition was to investigate the combustion of solid propellant, which is used for many rocket boosters during takeoff. A basic diagram of this propellant shows that it is made up of binder acting as a fuel and AP particles acting as an oxidizer. We were required to write an extensive literature review on the topic and develop an analytical model on MATLAB, which can be validated by experimentation and answers to the simulation. Starting off with our research, burning rate is the focal point, which basically is how fast the propellant burns linearly. It is an important area that is researched by many in this field due to it being a main contributor to rocket performance. A couple major variables that affect this burn rates that were the points of this research is oxidizer particle size, which is shown in the model to the right. As we can see, this increasing particle size leads to slower burning rates due to less surface area being shown for the fuel and oxidizer to react. Initial temperature also plays a role since reaction rate is a function of temperature and due to more energy being needed for the reaction to occur.
The tri-flame model was used to depict AP combustion. This model consists of three flames: the primary, the AP, and the diffusion flame. The primary flame is a dominating flame at low pressures. It is a premix flame depending on mixing and kinetics. The AP flame occurs from the gasification of the oxidizer. This flame is independent of mixing but dependent on kinetics. And finally, the diffusion flame is a combination of the AP and primary flames. The species reacting in this area consist of the product of the previous two flames.
Our analytical model overall is based on two phases as stated previously, of course being solid and gas phase. Mass conservation is assumed for all phases, so those equations can also be employed into our model. Surface geometry is also important, which is a function of pressure, oxidizer particle size, and oxidizer mass fraction to be calculated. This geometry will affect the reaction rates of the propellants. Energy conservation is, of course, the most important of the equations used. The sources of heat generation, which are from the three discussed flames, are used to find the heat release to the surface. Flame standoff is also calculated, which is the distance from the surface the heat release occurs, and diffusional distance, which is how far the particles must mix before reacting. These distances are used to calculate conduction to the surface, which helps us define a surface temperature, which can then be used to find the burning rates. These are the early results of MATLAB versus the Beckstead model, which was the major analytical model we studied to use to construct ours. These simulations were run at varying input pressures from atmospheric condition to about 4,000 psi and at a 20 micron particle size. We currently see a decent relationship at the first half of recorded pressures, but after around 100 psi of pressure, we deviate from this model. We have put extensive hours into the construction of this model and are still working day to day to get a 99% accuracy to the Beckstead model so we can confirm its validity and use it to compare our results to the experiments and ANSYS simulations.
The purpose of our experiment was to validate the analytical model. We additionally wanted to determine the effect of initial temperature and AP particle size on the burning rate of propellant. To do this, we burned samples of APCP with 90 micron, 200 micron, and 400 micron AP particles. For the 90 micron samples, we additionally adjusted the temperature from 244 Kelvin, 275 Kelvin, to 290 Kelvin. Our experimental setup is displayed on the right, where the electric match lights the propellant strand, and the whole process is captured on a camera and tripod. This is a video of the first trial of our experiment. It's played at 2 times speed, and it shows the propellant burning. The length between the two blue pieces of tape was measured, and the time that it takes the flame front to travel between these 2 points was recorded in the video. The burning rate can then be established by dividing the length burned over the time it took for the flame front to travel this distance. The propellant sample was 10 centimeters long and had a cross-section of 6 millimeters by 6 millimeters. The results of our testing are shown below. The first graph shows the burning rate versus particle size, and it clearly displays that an increasing particle size results in a slower burning rate, which intuitively makes sense. The smaller particles will act like a homogeneous propellant and create a premixed flame, which burns faster than the diffusion flames generated with larger particles. The relation from the temperature data was noisier, but the average trend still looks clear. It takes more energy to warm up and burn a colder strand of propellant, so the burning rate should decrease with increasing temperature. And that is what we found. The last element of our project is the 2D simulation. Here we assumed 2D flow, pressure-based, steady state. We additionally are using the multi-phase Eulerian model, the energy model, the laminar flow model, and the species transport model. Our methodology is to obtain and validate a steady state solution. After doing this, we will use the steady state results as initial conditions for unsteady numerical calculations with a regressive boundary. Our domain and our boundary conditions are depicted on the right. Thank you for your time.